Good morning, I am Marco Brighi, a research fellow from the Computer Science Department of the University of Bologna. Through this series of slides, I would like to present you our work entitled Metric Learning for Multilabel Classification. As indicated in the title, our work deals with multilabel classification. In a traditional classification problem, the main objective is to identify the class of the pattern. Multilabel classification represents a generalization of this problem, where several classes can be associated to a generic pattern. The belonging to one or more classes is described using a simple binary vector. In the context of multilabel classification, the classes are called labels to avoid any ambiguity with multi-class problems. Multilabel problems are already widely spread in some areas, such as natural language processing or computer vision. To solve these problems, it is possible to refer to two different strategies. On the one hand, solutions based on the transformation of the problem have been proposed, where a multilabel problem is transformed into a more canonical multi-class one. This offers the possibility to use all the knowledge already available for classification. On the other hand, it was decided to build specific solutions. For this purpose, traditional classification algorithms such as KNN or decision trees have been properly modified. The strategies based on the transformation of the problem are usually more performing, however, they are not applicable in every situation. Binary relevance and label power set are two of the most common problem transformation methods used to solve multilabel classification problems. The binary relevance approach trains a binary classifier for each label available. This means that to predict the labels of a single pattern, it is necessary to query all the classifiers involved. The label power set strategy creates a new class for each combination of labels inside the training set. These solutions are certainly optimal if the number of labels is limited. Otherwise, if the number is very high, for example a few thousand, the transformation of the problem could become difficult. Thousands of classifiers should be trained or thousands of classes should be considered. For these reasons, in certain situations, the choice of a native multilabel classification algorithm is mandatory. In our work, we propose a new method for improving the performance of a multilabel classifier based on learning a new embedded space for classification. Our proposal consists of three fundamental steps: clustering, metric learning, and classification. Thanks to the use of a clustering algorithm, groups of patterns are identified and used for learning a new metric capable of modifying the space. The patterns are then projected into the new space. Finally, thanks to a trained multilabel classifier, it is possible to start with the actual classification. The goal of the clustering phase is to find groups of patterns that share labels. Commonly, the clustering algorithm is applied in the feature space in which the descriptors of all patterns are present. If so, clusters would contain data with similar descriptors. That is not our objective. In fact, it is instead necessary to carry out clustering in the label space that contains the binary vectors of the patterns. HDBSCAN is the chosen clustering algorithm. It is a density-based solution that does not require a priori the number of clusters to find. Thanks to its flexibility, it can capture clusters with different density levels. As in any algorithm based on the calculation of distances, it is necessary to indicate the metric to be used. Considering the label space that contains binary vectors, the Hamming metric is certainly the most suitable. Using the previously identified clusters, it is possible to learn a new metric in a supervised fashion. Naturally, this operation takes place in the original feature space. The algorithm chosen for this phase is NCA, Neighborhood Components Analysis. It is a metric learning algorithm based on gradient descent, specifically designed to increase classification performance. Using this new metric provided by the algorithm, the distances between patterns belonging to the same class are reduced. On the contrary, the distances between different classes are maximized. At the end of this phase, a new space is available in which to project all the patterns and proceed with the classification task. In the last step, a multi-layer classifier is trained. Of course, the new space should be able to facilitate classifiers' tasks by maximizing performance. Multi-label k-nearest neighbors and random forest are the chosen algorithm. Multi-label KNN is one of the most known and used native multi-label classifiers. It extends the traditional KNN classifier and it uses Bayesian inference to select the labels to assign. Random forest builds a set of decision trees where each tree predicts the label to assign. To verify the effectiveness of our proposal, we used 3 different datasets. They are well known in the multi-label context. Enron is a dataset of emails labeled with a set of categories. Scene is an image dataset that contains visual descriptors of famous landscapes. The last one is the BibTeX dataset, which contains bibliographic data annotated with tags. The table in the slide shows some characteristics of the dataset taken into consideration. The datasets are sufficiently different from each other, allowing us to deeply test the potential of our proposal. The main and most known indicators in the field of multi-label classification are used, such as accuracy, precision, and recall. They compare in different ways the actual labels and those returned by the classifier. Thanks to their values, it is possible to evaluate the performance of our proposal. The chart in the slide allows to compare the results in terms of accuracy obtained by the two classifiers, in the original space, the blue line, and in the one built following our approach, the red line. MLKNN achieves better results in the new space across all 3 datasets. Considering the BibTeX dataset, for example, the improvement is more than 10 points. The results obtained by random forest are much more limited or absent. This result is not a surprise considering the characteristics of the proposed approach. The new space, by grouping different patterns, has evidently reduced the ability of the trees to discriminate with respect to a single label. Of course, it is possible to obtain the greatest benefits from the proposed approach if the classifier works with distance values, just like MLKNN. In fact, the new metric is built specifically for this purpose. In conclusion, a method for increasing multi-label classification performance has been presented. It uses a combination of clustering and metric learning to build a new space that facilitates the classifier's task. The results obtained from 3 different multi-label datasets confirm the effectiveness of the proposed solution. Based on this work, many possible future developments can be identified. It might be interesting to investigate the scalability of this approach using larger datasets. Furthermore, classic metric learning algorithms could be replaced by neural networks to try to achieve even better performance. Thank you for your attention and feel free to contact us at any time for more information on this work.